In this video, I'm going to talk you through how to prepare a halogenoalkane from an alcohol. If you'd like the notes that accompany this video, there is a link to the Crunch Chemistry website in the blurb below. Let's get started. This is the reaction that we are after. We are going to start with an alcohol, and we want to replace the hydroxyl group with a halogen in the form of a halide ion. So we're talking fluoride, bromide, chloride or iodide to produce the halogenoalkane, haloalkane, alkyl halide, and of course the hydroxide group is our byproduct. However, what we find is that the OH group is a really poor leaving group, which means essentially it is not very keen on breaking the carbon-oxygen bond and leaving. So, under normal circumstances, this reaction is not going to happen. What we need to do is activate the hydroxyl group so that it is much keener on leaving. The first method involves the reaction of the alcohol with a hydrogen halide. So we're talking, for example, HCl or HBr. And we're going to do this under acidic conditions, which is pretty straightforward because hydrogen halides are acidic when dissolved in water. Now, we know that alcohols are bases because the oxygen has a lone pair of electrons, and it just can't help itself. If there are hydrogen ions present in the solution, which there will be under acidic conditions, then this lone pair will come out and form a bond, a dative covalent bond, with the hydrogen ion. The result is an intermediate, so there's my methyl group, the oxygen, and it's now bonded to two hydrogen atoms, which means that it's lost its lone pair of electrons and it's now carrying a positive charge. So the alcohol has behaved as a base. In order to stabilize the positive charge on the oxygen is going to do what all electronegative atoms do and pull electron density away from the methyl group, which means that this carbon atom is going to be more delta positive than perhaps it was before, which opens it up to attack from the bromide ion. So the bromide ion is going to attack in the second step the delta positive carbon, and at this point the oxygen takes the pair of electrons out of the carbon-oxygen bond. Note that I've used a double-headed arrow to indicate the movement of a pair of electrons throughout this reaction mechanism, and it leaves. So in the second step from our intermediate, we are going to have the methyl group bonded to the bromine and water as our byproduct. The second way of activating the hydroxyl group in the alcohol is to carry out this reaction with phosphorus trichloride or phosphorus tribromide. So let's have a look at this reaction with PCl3. So we've got phosphorus bonded to 3-chlorine. Remember, each of these chlorine is very delta negative, which makes the phosphorus in the middle nicely delta positive. The alcohol once again behaves as a base. The oxygen uses a lone pair of electrons to attack the delta positive phosphorus in this first step, and one of the chlorine leaves, taking both electrons with it. So in the first step, we have an intermediate, so our methyl group bonded to oxygen. It's also bonded to the hydrogen still, and now we've got a strong bond between the oxygen and the phosphorus is bonded to 2-chlorine, and one of the chlorine left with a pair of electrons, so it's now a chloride ion, Once again, because the oxygen has lost its lone pair of electrons and is making 3 bonds, it is positively charged. Just as in the first method, we find that the carbon in the methyl group is also delta positive because the oxygen is pulling electron density away from it to stabilize its own positive charge, which makes it open to attack by a chloride ion. So chloride ion is going to attack the delta positive carbon. Remember that this negative charge here, let me just change colour, this negative charge here implies a pair of electrons, and this pair of electrons is what is going to be used to make the bond between the chlorine and the carbon. As a result of this attack, the carbon-oxygen bond is broken, and the electrons from the bond move onto the oxygen, replacing its lone pair. Once again, note how careful I am with the drawing and the placement of my curly arrows. The result is from the intermediate, we end up with chloromethane plus an OH group bonded to the phosphorus, which is still bonded to 2 chlorines, and this makes a good leaving group. And finally, the third way to go about this reaction and activate our hydroxyl group so that it becomes a good leaving group is to carry out the reaction with thionyl chloride. Thionyl chloride is SOCl2. And we need to do this in the presence of a base, but I'll come on to that in a second. To begin with, it's all very familiar. We have got our alcohol. Thionyl chloride is sulfur double bonded to an oxygen with 2 chlorines, so not unlike PCl3. These atoms are all delta negative, which makes the sulfur in the middle delta positive and open to attack from the lone pair on the oxygen. And once again, one of the chlorine leaves taking both the electrons in the bond with it, so that we end up with an intermediate. We have oxygen still bonded to the hydrogen with a strong bond to the sulfur, double bond O, Cl plus Cl minus. And once again, our oxygen is positively charged. In the second step in this reaction mechanism, a base with a lone pair of electrons abstracts, great word this, abstracts, i.e. nicks the hydrogen off this positively charged oxygen, and this hydrogen leaves without the pair of electrons. So the pair of electrons in the bond are returned to the oxygen as a lone pair. The base needs to be of medium strength. It needs to be strong enough to carry out this step that we require it to remove the hydrogen, but not so strong that it would have attacked the hydrogen when it was part of the alcohol. The result of our second step is another intermediate. So we've got the methyl group bonded to the oxygen, sulfur, double bond O, Cl. This carbon, of course, is delta positive because it's bonded to the delta negative oxygen, and that makes it nicely open to attack by the chloride ion. So chloride ion is going to attack and form a bond with the carbon. And we find the electrons in the carbon-oxygen bond are used to make a double bond between the oxygen and the sulfur. That in turn causes the sulfur chloride bond to break, and the chlorine leaves with the pair of electrons as a chloride ion. In step 3, we end up with our final products. So we have got chloromethane, methyl group to the chlorine, plus sulfur dioxide, SO2, plus the chloride ion. And this sulfur dioxide is an excellent leaving group. It's a gas, which means that it's going to be self-separating from the other products in the reaction, and also because it's a gas, we're going to have a large increase in entropy, which is going to drive the whole reaction forward. If this has been useful, then please hit the like button, subscribe and share. It makes a huge difference to a small channel like us. I look forward to seeing you next time.